Assalamu alaikum everyone. So today we will be having lecture number 17 and we will be talking about antennas and propagation. So what we will be following, we will be having review questions, and after having the review question we will quickly and fastly go through the topic that is relevant to the underlying review question, and in this way we will have a very quick and fast recap. So these are the topics which we will be going through one by one. The functions provided by antenna, and then after that we talk about isotropic antenna, that is an ideal antenna in order to have a reference for antenna functionality and design and so on and so forth. Then there are different radiation patterns that are associated with different shapes of different antenna. So we will be talking about those radiation patterns, and then we will be talking about parabolic reflective antenna. And antenna gain is an important factor that is also relevant to the antenna design and shape. And then after that we will talk about the signal loss in satellite communication. When we talk about the communication, data communication, so we come across noise because noise is omnipresent. So we will be talking about different types of noise. Then refraction, that is the mechanism relevant to the wave propagation, fading, and then diffraction and scattering of waves, and after that we will be talking about fast and slow fading, because there are different types of fading. So we will be talking about fast and slow fading, then flat and selective fading, and after that we will be talking about diversity techniques. So let's start. Here we have our first review question. So what are the functions that are being performed by an antenna? So let's talk about an antenna. So first we will try to establish the definition of an antenna. So in different books, different literature, you will be having different definitions of antenna. So we will be following IEEE definition over here. So according to IEEE, an antenna is a means of radiating or receiving radio waves. So it's a mean of receiving and radiating the radio waves. So you can say that in case of the receiving antenna, so it will be receiving energy, and in case of the transmitter it will be radiating energy into the atmosphere. So you can also define an antenna as a metallic device for radiating or receiving radio waves. So on the right hand side of your picture you can see that we have the source, right, and then we have the transmission lines, because there must be a transmission line between the source and the antenna, so that the antenna is able to radiate the energy or waves, EM waves, into the atmosphere or free space. So we have the transmission line, and then after the transmission line we have the antenna. So over here you can see that we have cut the transmission line and bent in such a way that it is acting as an antenna, right? So after that we will be having the radiated energy, or you can also say that it's a radiator free space wave. So this is a very general and standardized way of mentioning or defining an antenna. So after establishing the definition of an antenna, we already have gone through that the antenna size is correlated with the wavelength of the underlying communication, right? So our requirement, one of our requirement regarding the communication system, that we want that the antenna should be absorbing or radiating maximum energy at one angle, or maybe it is suppressing the radiated, receiving or transmission energy in all other direction, or maybe in other directions, right? So this is one of the requirement, right? And then we also wish that in addition to the directional device, antenna should also be acting as a probing device, right? So there are different requirements in order to construct an antenna. We need a conducting wire and a aperture, a patch, and assembly of elements. These are called arrays, a reflector, a lens, and there are other number of elements that are required in order to construct an antenna. So whenever we talk about the wireless communication system, or the mobile communication system, or maybe some other satellite communication systems, the antenna, they play a very critical and vital role. So you can say that the antenna serves to a communication system the same purpose that eyes and eyeglasses serve to a human being, right? So we are having some basic functions of antenna. So it radiates energy into the space, and it absorbs energy from the free space. So it resides between cable waveguide, right, and the medium air. The main function of the antenna is to match impedance. So we can also say, because free space is having, for example, one impedance, and the transmission line or the terminating ends of the underlying transmission line that is being used as an antenna, so they are having another impedance. So it's the functionality, one of the functionality of the antenna, to match the impedance in order to radiate the maximum energy into the free space, and in case of the receiving antenna or receiving side, it should be absorbing maximum energy from the free space. So it can only be possible when there is an impedance match between different media, right? So one medium is free space and the other medium is the metallic wire. So you can also say that antenna is also acting as an impedance transforming device. And the second and one of the important functionality of an antenna is to radiate energy in a desired direction, right? So as mentioned that if we have directional communication, so we want or we wish that the antenna should be radiating maximum energy in one direction, and it should suppress all energy in all other directions. So right, so this is one of the key function, that it radiate maximum energy in one direction and it radiate minimum energy in all other direction. So after having the basic functions of antenna, so we will be talking about the advanced functionality provided by the antenna. So here we have four primary functions, advanced functions provided by the antenna. So it can act as a filter, right? So here we have spatial filter, antenna acting as a spatial filter, that is directionally dependent sensitivity. And then we can also we can also have antenna as a polarization filter, right? So it will be actually taking or accepting the certain radiation patterns, and it will be suppressing or stopping some other radiation patterns. So polarization dependent sensitivity. And then impedance transformer. So as mentioned that we have to radiate energy into this free space, so those two different medias, they will be having different impedance. So antenna has to act as a impedance transformer, so transition between free space and the transmission line, right? Then propagation mode adapter. So we can also have free space and the waveguides, right? So in that case, antenna should be acting as a propagation mode adapter. So let's have the details. So antenna as a special filter. So it has the property of being more sensitive in one direction than in another direction. That is already mentioned. So as a result, antenna is actually providing the ability to spatially filter signals from its environment. So it is more sensitive or aligned to a particular direction. So in that way, it is actually receiving maximum energy from the waves or from the environment in that direction, and it is receiving very little energy or no energy, you can say, in all other directions. So that is in the case of line of sight communication. So here you can say that antenna is acting as a spatial filter. And then we can also have the polarization filtration capability of the antenna. More sensitive to one polarization than the other polarization, that provides the ability to filter signals based on its polarization. So for example, if one beam of signal is polarization in one way and the another beam of EM waves is polarized differently, so antenna can be aligned in order to act as a polarization filter. So it will be receiving the polarization of its setting, right? Then impedance transformer. So if we talk about the intrinsic impedance of free space, that is E over H, and then we can also define the characteristic impedance of the transmission line, that is V over I. So of course these two expressions are mentioning that there is a mismatch, impedance mismatch between the free space and the transmission line. So it's the antenna who is transforming the impedance from free space to the transmission line when we are talking about the reception, and when we talk about the transmission, so it is transforming the impedance from transmission line to the free space. So here we have propagation mode adapter. So antenna as propagation mode adapter. So in free space, the waves spherically expand by following one of the principle that is called Huygens principle. So according to Huygens principle, each point of an advancing wave front is in fact the center of a fresh disturbance and the source of a new train of waves. So within the sensor, the waves are guided within a transmission line or waveguide that restrict the propagation to one axis. So here you can see the propagation mode adaptation. So during both transmission and receive operations, the antenna must provide the transition between these two propagation modes. So this is the transmitting antenna and this is the receiving antenna. So here we have you can see the alignment of the modes of propagation, plane waves, and here we have E waves, so trapped transition. Here this is the transmission line source that is generating the energy in order to have the EM waves or waveguides. So in between we have the free space. So you can see that the propagation mode adaptation of an antenna, and it is very much clear from the alignment of the waves. So here we have different purposes of antenna. Again, antenna can also function as a transmission line, radiator, resonator, right? So unavoidable for broadband application, resonance must be attenuated, right? So after quickly going through the antenna functionalities, we can now answer the review question. So we will be talking about two functions that are very important for a transmission of a signal. The radio frequency electrical energy from the transmitter is converted into the electromagnetic EM energy by the antenna and radiated into the surrounding environment, right? So this is one functionality. In order to have the transmission, we have to convert the electrical energy into the electromagnetic energy. So this is, and that energy has to be radiated into the atmosphere, free space and water. And if we are talking about the receiving antenna, for reception of a signal, EM energy that is being incident on the antenna has to be converted to the radio frequency electrical energy. So we are receiving EM energy from the atmosphere, from the free space, from the water, and then we actually, antenna is receiving that energy and is transmitting or conveying it to the system by transmission line. So here we have another review question. What is an isotropic antenna? So isotropic antenna is actually a reference antenna, or you can say an ideal antenna that is not exist physically. So it's a concept, you know, and this concept is used in order to have reference to describe real antennas, right? So we can say that or define isotropic antenna as an antenna that is radiating energy equally in all directions, and that is not the case when we talk about the real antenna. So its radiation pattern is represented by a sphere. So you can see in the figure on your left hand side, and whose center coincides with the location of the isotropic radiator. So reference antenna for gain. So isotropic antenna is used as a reference antenna in order to calculate the gain of the real antenna, or the antenna that is going to be designed or used for the underlying communication system. To our reference antenna, isotropic antenna often used gain over isotropic. So radiates power ideally in all directions, and gain is calculated in dBs. Test antennas field strength relative to reference isotropic antenna at same power, distance and angle. So the best example, a lamp is similar to an isotropic antenna, because if we talk about the lamp, so it's almost radiating same energy in all directions. So here we have mentioned different antennas, their shape, gain and bandwidth and radiation pattern. So you can see the isotropic antenna, and this is the point source, and it is radiating equally in all directions. Gain over isotropic antenna 0, right, because this is the reference. So beam width, it's 360, right, so it's not possible. And then this is the radiation pattern, and we can also have radiation pattern and beam width and gain and shape of some other antennas. So every real antenna radiates more energy in some direction than in others, right? So in directional properties, so idealized example of directional antenna, the radiated energy is concentrated in the yellow region, right? So you can see here the radiated energy is concentrated in this cone. directive antenna gain, the power flux density is increased by the inverse ratio of the yellow area and the total surface of the eyelet. So gain in the field intensity may also be considered. It is equal to the square root of the power gain, right? So the conclusion over here is that the radiated energy is concentrated here in case of the isotropic antenna. You can see that the cone. So here how we measure the antenna gain. So you can see we place reference antenna in first step, and then we measure the gain, right? And in the second step we replace the reference antenna with the actual antenna, and here we have the measurement equipment, and we then can calculate the gain. And antenna gain is P over P naught. P is the power delivered to the actual antenna, and P naught is the power delivered to the reference antenna, right? Okay, so here is the answer, is a point in space that radiates power in all directions equally, and that is not the case. So we are actually required or needed in order to have a reference. So here we have another review question regarding radiation pattern. So what information is available from a radiation pattern? So first we have to talk about the radiation pattern. When we talk about the antenna or this antenna design, the term radiation pattern refers to the directional dependence of the strength of the radio waves from the antenna to the other source. So the next question is how we can calculate those different radiation patterns. So we can have the far field pattern analysis and the near field pattern analysis. So there are different computer programs, and we can also use different techniques and tools in order to have the radiation pattern. So here we will be talking about radiation pattern in more details, graphical representation of radiation property of an antenna. So we normally have two dimensional radiation patterns, right? And the radiation pattern of an antenna, it's actually a plot of the far field radiation from the antenna, and more specifically it is a plot of the power radiated from an antenna per unit solid angle, or its radiation intensity U, right? So so again radiation pattern, then power pattern versus field pattern, and we can also have normalized radiation patterns. So usually the pattern describes the normalized field, right? So we can normalize the power. So here you can see the 3D pattern. 3D plot of antenna pattern assumes that both angle theta and phi varying, which is difficult to produce and to interpret, right? So we need a 3D representation. So here we have 2D radiation pattern, and this is the example, a short dipole on z-axis elevation plane, and we can also have E plane and H plane. So this is another example. We have a horn antenna, and you can also see the alignment of the electric and magnetic field, the radiation pattern, and antenna mask, another example. So now we can answer the question, is a graphical representation of the radiation properties of an antenna, right? So you can see that we have different loops. These are called side loops, and this is the main loop, and this is the back loop. And here we have mentioned the pattern, radiation pattern in Cartesian coordinates, and here we have the radiation pattern in polar coordinates. So in polar coordinates, you can see it's rather easier to have a look and to conclude when we talk about the radiation pattern. Graphical representation of the radiation properties of the underlying antenna as a function of space coordinates, right? So another review question, what are the advantages of a parabolic reflective antenna? So first we will be talking about the purposes of antenna, generally impedance matching. So before talking about the reflective parabolic antenna, so let's talk about the two main purposes of antenna. First, antenna is used to have the impedance matching, and then antenna is also used in order to have a directed radiation, or you can say in order to have a desired directional radiation. So a parabolic antenna is a high gain reflective antenna. So it is used for television communication, radio communication and data communication, but it can also be used for radar on ultra high frequency and SHF sections of the electromagnetic spectrum. So here we have the reflective antenna. So you can see here is the parabolic reflective. So this is a sort of parabolic shape, and here we have the focus, primary radiator, and such as parabolic antenna are composed of a primary radiator and a reflector. So this is the primary radiator, and this is the reflective surface or reflective mirror, or the radiations that are incident over here, they will be reflected back to the focus or the primary radiator. So any electromagnetic wave that is incident upon the paraboloid surface will be directed to the focal point. Primary antenna is used at the focal point of the parabolic reflector antenna instead of isotropic antenna. The isotropic antenna would radiate and receive radiation from all directions, resulting in spillover. And finally, primary antenna should be designed in order to illuminate just the reflector uniformly. So here we have shown the loss in case of parabolic antenna. So you can see that this is a sort of spillover, and here the reflections are not being directed towards the focus, right? So they are showing the loss. And here we have the characteristics, aperture pi r square, where r is the radius of the diameter, and if we have a large disk, so we have more gain, right? And clear line of sight is important in case of parabolic antenna. So I will skip those calculations. So here are the advantages of the detailed advantages of the parabolic antenna. So here we have the answer to our question. Parallel beam without dispersion in practice, because this is the theory, right? So but in practice, in application, there will be some beam spread. Nevertheless, it produces a highly focused directional beam. So antenna gain. So we have a question regarding the antenna gain. So what factors determine antenna gain? Antenna gain, you can also define it or say it directivity, power output in a particular direction compared to that produced in any direction by a perfect omnidirectional antenna. So we call it an isotropic antenna, right? it doesn't, antenna gain does not increase power, only concentrates effective radiation pattern. So effective area is also important when we talk about the antenna gain, expressed in terms of related to physical size and shape of the antenna related to the operational wavelength of the antenna. So we have two different types of gain, passive gain and active gain. So focusing isotropic energy in a specific pattern. So this is a very good example. So when we focus the dispersed beam of waves from sun by using some prism, and we can have a fire, right, on a paper or maybe on a wood. So then we have so again passive gain. Passive gain, total amount of energy emitted by antenna does not increase the distribution of energy around the antenna. Antenna is designed to focus more energy in a specific direction. So again, directivity is always a function of the antenna, that is independent of the components leading up to the antenna. So we have certain advantages. Does not require external power. As the gain increases, its coverage become more focused. Highest gain antenna can't be used for mobile users because of their tight beam. So here we have the active gain. After mentioning the passive gain, we need external power source, amplifier, high gain transmitters. Active gain involves an amplifier, right? So here is the relationship between the antenna gain and the effective area. So G is gain 4 pi AE lambda square, where A is the effective area, G is the antenna gain, F carrier frequency, because we have seen lambda, so lambda and F, they can be related. C is the speed of light and lambda is the carrier wavelength. Okay. So antenna gain and effective areas, isotropic, power gain is 1. So here we have the answer, very precise answer. So the factors that actually determine the antenna gain, they are the effective area and the wavelength. If I go back, right, so you can see here 4 is constant, pi is constant, and rest of the factors, antenna area, effective area, and the lambda, that is the wavelength. So effective area and wavelength. So now we have a review question from satellite communication. What is the primary cause of signal loss in satellite communication? So first we need to understand how satellites work. So we have two stations on the earth and they want to communicate with each other, right? But they are not within their line of sight. So what we can do, we can launch a satellite and we can have a transponder there that is receiving a signal from one station on the earth and will be transmitting or repeating the same signal to the other station on the earth, right? So this is the way how we use satellite communication. On the earth want to communicate through radio broadcast, but they are too far, they are not in their reach or line of sight. Two stations can use a satellite and a relay, right? So the satellite which we have launched, it can use a transponder or it can be a relay station for their communication. Sends a transmission, so we have our uplink and downlink. If we talk about the, this is called on one earth station sends a transmission to the satellite, this is the uplink. The transponder converts the signal and sends it back to the second earth station. It's called downlink. So there are certain advantages that are associated with the satellite communication. The coverage area is very, very long, right? And the transmission cost of satellite is independent of the distance from the center of the coverage area. And there is another advantage, that satellite to satellite communication is very precise, because when we talk about the GPS, we need 3 or more satellites in order to have the correct and exact position. So that's why the GPS system is accurate, because the satellites that are being used in order to identify the position, they are very precise. Higher bandwidths are available when we talk about the satellite communication. So there are certain disadvantages of satellite communication as well. It's costly, so whenever we want to launch a satellite, so it is costing a lot of money. Satellite bandwidth is gradually becoming used up. There are larger propagation delay because of the satellite. So there are some basic factors that has to be taken into account when we talk about the satellite communication. Elevation angle. So this elevation angle is actually affecting the satellite coverage area. So normally we want, or we wish, the elevation angle of 0 degree. So by having the elevation angle of 0 degree, the transmission beam they can reach the horizon visible to the satellite in all directions. However, due to the environmental factors like object blocking, the transmission, atmospheric attenuation, and the electrical background noise, there is a minimum elevation angle of the earth stations. So I'm skipping. So there are different impairments when we talk about the satellite communication: atmospheric loss, absorption and attenuation, and then ionospheric disturbances, right? So traveling ionospheric disturbance are clouds of electrons in the ionosphere that provoke radio signal fluctuations, which can be as a statistical basis. Okay, so here we have the answer. So the main or primary cause of signal loss in satellite communication is free space loss. So when we talk about the communication system, so we have to face certain impairments, right? And one of the impairments is noise, right? So if we talk about the significant impairments, they are attenuation, delay distortion, and attenuation, distortion, and noise. So here we will be talking about the noise. So signal strength falls off with the distance over any transmission medium, and it can also, signal can also vary with frequency. So noise is actually defined an unwanted signal inserted between transmitter and receiver. So noise is the major limiting factor in communication system performance. So there are different types of noise. Thermal noise, that is also called Gaussian noise, due to thermal agitation of electrons, and this noise is uniformly distributed across the bandwidth, and it is also referred to as white noise or Gaussian noise. Then we can also have intermodulation noise produced by non-linearities in the transmitter, receiver, and or intervening transmission medium, and effect is to produce signals at frequency that is the sum of difference of the two original frequencies. So actually when we talk about a signal, so it is actually composed of different frequency components. So crosstalk, then we can also have impulse noise. So here we have mentioned noise generally thermal agitation of electrons present in all electronic devices as a function of temperature, so uniformly distributed across the frequency spectrum. So here you can see the presence of noise in bits, right? So this is data that is actually transmitted, or you can say signals, right? And data is represented by using digital waveforms. Noise, signal plus noise, so this noise is added. So here we have signal plus noise. We have added these two, and then after that we receive this data 1 0, right? So you can see that this bit has been changed, again this bit is again changed. So now you can have an idea of errors in bits. So here is the expression for the thermal noise. N naught is equal to kT, noise power density, right? K Boltzmann constant, T is the temperature. Okay, and now we can answer the question. Is due to thermal agitation of electrons, and intermodulation noise produces signals at frequency that is the sum or difference of two original frequencies or multiple of those frequencies. Crosstalk is unwanted coupling between signal paths. Impulse noise is non-continuous, consisting of irregular pulses or noise spikes of short duration and of relatively high amplitude. So 4 different types of noise. So here we have another question. What is refraction? So if we talk about the refraction, because when we are discussing wireless communication, so the medium is free space, and the energy which we are actually using in order to convey our data from one point to another point is the electromagnetic energy. So light is also a form of electromagnetic energy. So the same laws, or you can say most of the laws that hold in case of light, they will be holding in case of EM wave propagation, right? So law of refraction, right? So as we know that when light or EM wave enters from one medium into another medium, so it bends from its normal. So this is the normal, and this is medium N1, and another medium with a refractive index of N2. And this is the incidence angle, and this is the refracted angle. So normally this should be the path, or naturally, but you can see that it bends from its original position, right? So this is the relationship. If we talk about the law of refraction, N2 sine theta 2, N1 sine theta 1, right? And they are the index of refraction for different media. So here we have shown refraction. RF signal changes speed and is bent while moving between media of different densities, right? So RF signal. So here we have clouds. So again the density is changed, and you can see the refraction, right? So it's bending. So again here we have shown bending in particles and bending in waves, refraction of particles and waves, right? And refraction is the bending of radio beam caused by changes in the speed of propagation at a point of change in the medium. So you can see here there is a point of change in medium, and you can see the bending of the RF wave. Again here different media, different densities, and you can see the refraction. So fading, what is a fading? So fading refers to the time variation of received signal power caused by changes in transmission medium or paths. So there are certain reasons of the underlying fading: atmospheric conditions such as rainfall. We have different types of fadings: fast fading, slow fading, flat fading, selective fading, and relay fading, right? And here we have some of the details, right? And like flat fading, independent from frequency; selective fading, frequency dependent fading; and relay fading, no dominant path; and Riccian fading, line of sight is dominating, plus presence of indirect multipath signals. So now we have our answer of fading quickly. Term fading refers to the time variation of received signal power caused by changes in the transmission medium or paths. So here we have to mention the difference between diffraction and scattering. So again, these are the mechanisms that are relevant to the wave propagation. So here we have mentioned diffraction, direction or intensity of a wave as it passes by the edge of an obstacle. RF signal slows down as it encounters the obstacle and causes the wavefront to change direction. Diffraction is often caused from buildings, small hills and other large objects in the path of the propagating RF. So here you can see diffraction at the edge of an impenetrable body that is large compared to the wavelength of the radio wave. So here we have another version of diffraction. So you can see multiple refractions is called scattering. Strikes an uneven surface causing the signal to be scattered. The resulting signal are less significant than the original signal, right? So you can see multiple scatterings. RF signal hit an object whose size is in the order of the wavelength of the signal or less, right? So here we have shown multipath propagation mechanisms, reflection, scattering and diffraction, right? So here you can see refraction and here you can see is bending from the edge, right? So you can see the bend from the edge. This is scattering and diffraction, right? So bend from the edge is diffraction and here we have the scattering. So answer for diffraction and scattering: diffraction occurs at the edge of an impenetrable body, right? So if I go back, so actual path can be this. If here we have the source and you can see that this is bending, the RF wave is bending at the edge, right? And then we have scattering, right? So you can see the scattering is multiple reflections, right? So multiple reflections, right? If the size of obstacle is on the order of the wavelength of the signal or less, scattering occurs, right? So here you can say that this object size is comparable to the wavelength or less, right? So that's all for today's lecture. So today we have a recap of the chapter which we were studying, antennas and propagation. So we talked about antenna functions, isotropic antenna, radiation patterns those antennas are providing. Then we talk about one of the specific antenna, that is parabolic reflective antenna. And then there are different characteristics that are very important when we talk about the antenna design. So we talked about one of the characteristic, that is antenna gain. And then we have also addressed satellite communication, and we have taken one review question from satellite communication that is relevant to the signal loss, and the DAVL, that is the noise which is omnipresent whenever we have to communicate data from one point to another point. So we have discussed different types of noise, and then we have different propagation techniques and mechanisms that we should be able to understand, and in order to have a good antenna design. So these are refraction, fading, diffraction and scattering. So we have talked about all these concepts. So that's all. आज के लिए इतना ही काफ़ी है मेरी तरफ से. अल्लाह हाफ़िज़, अस्सलाम वालेकुम. So let's have complementary session for lecture 17, that is antennas and propagation. So we will start from antenna gain. So here we have some of the formulas that are used in order to calculate the gain for antenna. So you can see 4 pi AE lambda square. So here the parameters which are used: G antenna gain, AE is effective area of the antenna, carrier frequency, and c is the speed of light, that we know that it is constant, and lambda is the wavelength, carrier wavelength. So for a parabolic reflective antenna with a diameter of 2 meter operating at this frequency, that is 12 gigahertz, what is the effective area and the antenna gain? So we have an area of pi r square, because r is unit, right? Diameter is 2, and we can have r divided by 2, so is 1. So we are left with pi, that is the effective area, right? So that is the area. And now we have to calculate the effective area, and that is 0.56 pi, and the wavelength relation for wavelength is lambda is equal to c over f. So the wavelength becomes 0.025 m, right? So then we can calculate the gain, right? 7a over lambda square. So we know the value of pi, so you can see that 7a over lambda square. We are using this formula, and the gain becomes 45.46 dB. And here we have another question. So we have a table, so where we have the type of antenna, effective area, and the gain that is calculated relative to isotropic. So we take the isotropic antenna as the reference antenna that is radiating equally in all directions. So that is not the case, so we are using this as a reference. For each of the antenna type listed in this table, what is the effective area and gain at wavelength of 30 millimeter, and we have to repeat the same question for a wavelength of 3 millimeter, and we have to assume that the actual area for the horn and parabolic antennas is pi m square. So here is the type of antenna, effective area, and power gain, and remember that we are using isotropic antenna as the reference antenna. So here you can see we have G. Again we are going to use the same formula, 4 pi AE over lambda square, 4 pi f square AE over c square, where G is the antenna gain, AE effective area, and F frequency, c speed of light, and lambda is the carrier wavelength. So by using the formula, we just have to put the values, and we can calculate the gain, right? So that's effective area, right? And gain at wavelength 30 millimeter. So we can calculate the gain, and this is the effective area. So this is the effective area for lambda is equal to 30. This is the effective area for lambda is equal to 3, and we have also calculated the gain. So you can see for the isotropic antenna, the gain is unity. So that's why we take this as a reference, and that's why we say that it is radiating equally in all directions, right? So we just have to place the values, right? So we have another question. The maximum distance between two antennas for line of sight transmission is 1. If line of sight transmission, if one antenna is 100 meter high and the other antenna is at the ground level, right? So we can use the formula D is equal to 3.57 kh, right? And by putting the values, we got 41 kilometer distance. And now we have to suppose that the receiving antenna is 10 meter high. To achieve the same distance, how high must the transmitting antenna be? So again, here we know the distance, and we are using the this formula kh1, and this is 13.3, and here we can calculate the height of the antenna, that is 46.2. Okay. So now we have another question. We have to find the isotropic free space loss at frequency 4 gigahertz for shortest path to a synchronous satellite from Earth, and this satellite is at a distance 3586 kilometer at 4 gigahertz. The wavelength is 3 into 10 raised power 8, right? So we are going to use the formula C is equal to F over lambda. So then we have, this is the loss in dBs, 20 log lambda, and this is 20 log d, that is the distance, and this is the AT and AR, right? So we just have to replace the values. So you can see we are placing values, and the loss becomes 195.6 dB. Antenna gain of both the satellite and ground base antennas, right? Typical values are 44 dB and 48 dB respectively. So now we are calculating the free space loss, right? So 195 minus 44 minus 48, so 103.6. Transmission power of 250 watt at the Earth station. What is the power received at the satellite? So into dBs, so the power at the receiving antenna is 24 minus 103.6, so that is the power. So here we have the thermal noise. We have the formula for thermal noise, N naught is equal to KT, N naught noise power density in watts per 1 hertz, Boltzmann constant, and T is the temperature in kelvins, right? So that is the watt per hertz. Room temperature is usually specified at T is equal to 17 degrees centigrade or 290 K. At this temperature, the thermal noise power density is, so here we have to place the values. We know the Boltzmann constant, temperature is already given, right? So we can calculate the noise. This is the thermal noise. So now here is the expression for energy per bit over noise energy, right? So you can see we have EB over N naught, S over R, and you can have this formula by replacing the value of N naught, and we can also represent this in decibels, right? So S dB, 10 log R, 10 log K, and we are taking actually log on both sides, right? So here we have the question. After discussion of EB over N naught, encoding technique requires that EB over N naught is equal to 8.4 dB for a bit error rate of 10 raised to power minus 4, 1 bit error out of every 10,000. If the effective noise temperature is 290 K and the data rate is 2400 bits per second, what received signal level is required? So we need to find the level of the signal. You can say the power. So 8.4, right? This is EB over N naught, right? So this is in dB, and after that we have to use the values. 2400, that is the data rate, so you can say this is the rate, and here we have the 228.6, right? So this is again already Boltzmann constant, right? And here we have the temperature 290 K, and after placing the values we find out that S is equal to minus 161.8. So another question, it is often more convenient to express distance in kilometer rather in meters and frequency in megahertz rather than hertz. So we have to rewrite the equation using those dimensions. Equation from textbook, we know this is the transmitted power and this is the received power. We know this is equal to 20 log 4 pi d over lambda. So 20 log lambda, 20 log d, and 21.98 dB. So now we can see that we are going to use to represent, right? So this is again, if we use the representation, right? So f and here d. So we have used the formula over here, that is equal to c is equal to f over lambda. And now we are going to represent this equation by using the dimensions 20 log f megahertz, 20 log d kilometer, plus 60 minus 147. So you can see that now we are having the equation, but the dimensions are in frequency in megahertz and distance in kilometers, right? So here we have another question. Produces 50 watt of power. Express the transmission power in units of dB and dB watt. So if the transmitter's power is applied to the unity gain antenna, 900 megahertz carrier frequency, what is the received power in dB? At free space distance of 100 meter, repeat B for distance of 10 kilometer, C but assume a receiver antenna gain of 2. So here is the solution, right? So you can see power, we have the formula, we just have to replace the values, and again for B we have the formula, we just have to place the values, and we have to repeat distance, change the distance, and for D receiver antenna gain. So here we will be going to change the gain. So here we are dealing with the free space loss, power transmitted, and this is the received power at the receiver side, and that is equal to 4 pi d square over lambda square, 4 pi d whole square, lambda carrier wavelength, frequency, d propagation distance between two antennas, transmitting antenna and receiving antenna, c is the speed of light. And here we have represented those formulas by using, so L, that is the loss, right? 10 log power transmitted, power received, right? So, and now we are expanding, so we are actually going to represent this in dBs. That's all for the complementary session.